For our final topic in this waves unit, let's talk about how different waves can operate as they encounter a barrier or a wall or a change in the medium. Today's focus is going to be on the reflection, refraction, and diffraction of waves. Now, everything that we're going to talk about today can actually operate for both light and for sound. More often, we think of these as light transformations, but all of these can go for really any type of wave as well. So the first one that I want to talk about is something that you have definitely experienced before, and that is reflection. We define reflection mathematically in terms of angles. That we say that the angle of incidence here just being a fancy word for saying the light coming in or the wave coming in, must equal the angle of reflection. Now, something that's interesting here in the physics of this all is where that angle is actually being measured from. Now we have a little dotted line here that's perpendicular to the surface. Let's say that the surface is a mirror. Now that dotted line represents the normal line. Normal is just a mathematical term that means perpendicular to. So the normal line is perpendicular to the surface, and we measure this angle of incidence and angle of reflection in reference to that normal line. Now, it doesn't really impact us too much, especially in this class. We're not going to be dealing too much with the math of this all, but you'll see here that I've indicated these angles in reference to the normal line, and then given a little dash here to represent maybe the geometry that you've had, showing that those two angles are equal to each other. So this is really kind of a common sense understanding of how the world works. If you had something, whether it was a ball or a ray of light that bounce off of a surface, you expect them to bounce in a way that you would be able to predict. So here bouncing in, we would leave that surface at an angle that is the same as the angle you came in, the angle of incidence. If you had a nice shallow angle like this, you would expect it to bounce at a nice shallow angle as well. The most common example that we think of for reflection is just a simple mirror. In a mirror, the light bounces off of the mirror and back at us so that we can see our reflection in it. Now, not every surface is actually a flat mirror. Even surfaces that seem really smooth, like the wall here behind me, seems pretty smooth, but it doesn't operate as a mirror. I don't see my reflection when I look in that wall. And that's because even smooth surfaces are often textured on a more molecular level. Now, all of these light rays are bouncing in the same way that you would expect, reflected over that normal line. Now, these ones are as well. The only difference is that normal line is pointing in different directions depending on what the localized part of the surface is looking like. If you have a little bump, it's going to affect the way it bounces. Kind of like if you've ever played a ball where you're trying to catch a ball that bounces off the ground, it's going to bounce differently if it hits a bump. We call this type of reflection diffuse reflection. Basically means that you can still see the object. The only reason you see the wall behind me is that light is bouncing off it. It's just not bouncing off perfectly parallel to the way that it's coming in. So you're not seeing it as a perfect reflection. You're just seeing the light as it bounces in a diffuse manner. Our next transformation that I want to talk about is a little bit more interesting here. Refraction is when light bends, and specifically when it bends because of a change in the medium. So you've often seen this as it goes through water or goes through glass or some sort of prism. One great way to see the effect of refraction is to fill just a jar filled with water. Now the light, it bends as it goes from the air into that water boundary. And if you hold it up to your face, you can see that light bending as it's going between that medium boundary change. Another great way to see the property of refraction is to take a glass of water and fill it up, and then just put a marker or a pencil in it. And you can see that the boundary difference between the air and the water looks like this pencil or this marker is broken. In fact, it isn't broken. You're just seeing the light bend differently as it goes through air versus water. One thing that I want to mention, specifically related to this prism part, is refraction changes depending on the wavelength of that light. So you'll see that the different colors bend differently as it's going through a prism here. Or if you think of it as like a raindrop acts like a prism. So the only reason that we see rainbows, this separation of colors of what's normally white light, is because of the refraction of that light as it goes through the little droplets of water in our atmosphere. Now, this refraction, this bending, is happening because the speed of the wave is different in different mediums or different media. Light, for instance, moves slower in water than it does through air. And you can see that change. If you have one medium that's different than the other, so air to glass or air to water, you see a pretty significant change. We saw a couple examples of refraction as it was bending from a medium change, so air into water. We saw the light bending. Now, the reason that the light bends is because the optical properties between those two are very different, and light travels at a different speed in air than it does in water. Now, it turns out there are some materials that have a very similar optical properties. For instance, canola oil has almost the same index of refraction, the same optical property or speed of light as Pyrex glass. Now, if I place this Pyrex measuring cup here in this container filled with canola oil, you can still see it in there because there's some boundary change between the glass and the air that's inside it. But if I fill that Pyrex measuring cup with canola oil, we can see that since the canola oil has the same optical properties as the glass, it essentially disappears because there is no longer any bending between those medium changes. So to give an interesting visual to this, for a good way that you could like predict how that light is going to bend is I like you to imagine that you're pushing a two-wheeled lawnmower or just something with two wheels kind of connected with one axle. And this lawnmower is going from something that it travels easier in to travel something that's traveling harder in. This N terminology over here is not something that you need to worry about for this particular course, but that's something known as the index of refraction. Basically, it's just a measurement of how easy or hard it is for that substance, for light to travel through that substance. So N of 1 is air. Light travels faster in air than it does through water. Water has an index of refraction of about 1.33. So imagine that you're pushing that lawnmower through a medium that it's easy to travel in. We're going to see it travel down that ray until one of the wheels hits the next medium. Now, this medium, being water, it allows light to travel slower than it did in air. And if you were pushing a lawnmower and one of the wheels hit a piece of dirt or mud or something that it moves slower in, it's going to cause that wheel to slow down while the other wheel continues to move at the same speed. So what's going to happen there is you're going to get that lawnmower to start to bend. You're going to bend towards the wheel that slowed down. Then this other wheel also hits that boundary, and since both of them are now in the water, or in the mud, if you will, they're going to travel at the same speed and continue off down the road. So let's see that animation one more time. You travel down to the boundary, one wheel slows down, and then the other wheel hits there as well and continues off in that same direction. The light will always bend toward the more optically dense medium's normal line. It's just a fancy way of saying that the light in this case is going to bend downward as it goes from air to water. Our third type of transformation that I want to talk about in terms of waves is one of the harder ones to really think of examples for, and one that maybe isn't as obvious to you in your everyday lives, and that is diffraction. Diffraction happens when waves bend as they move around a barrier. So a common example is just using water waves. If water waves were impacting this wall here, but there was a gap in the wall, the water waves don't just travel straight through that gap. Instead, they emanate outward in every direction from that new source, basically. So That means that if you were swimming here, kind of behind the wall, you would still experience that wave because it's bent around that barrier. A couple of other illustrations of this as going through this gap in the wall or going around a barrier. So have you ever wondered why a shadow is fuzzy? It turns out that it has to do with diffraction. We're going to do a quick demo here with just a flashlight and a white sheet of paper to show diffraction in real life. If you take a flashlight and you hold it above a sheet of paper and then you put your hand between the flashlight and the paper, your hand obviously casts a shadow on that paper. Now if you look at the edge of that shadow, you'll notice that the edge is rather fuzzy. The reason for this fuzziness is diffraction. You can actually see, even if you try to pinch your fingers together, you get these interesting light spots and dark spots that form around your fingers. Now the reason for this is light is bending around the boundary of my fingers, and not all of it is being blocked in the areas that you would expect it to. The bending of light around this boundary is known as diffraction. I want to close with some more examples because these reflection, refraction, and diffraction, these happen in your everyday lives all around you. And it is important that you can identify for this class where each of these are happening. So one example is a rainbow. We talked about that earlier in this video, that a rainbow is an operation of reflection. I want to conclude here by going through some more examples. As I've mentioned, there are actually many different examples of these reflection, refraction, and diffraction in your everyday lives. And sometimes it's hard to pick out, okay, what's exactly happening here? Like, how does this work? Which of these three is it? So the first of these examples that I want to talk about is one that we've actually mentioned already, and that's a rainbow. A rainbow happens because light is bending differently for different wavelengths of light. So the different colors bend at different amounts as they travel through a change in the medium. A rainbow is happening when the change in the medium is going from air through water, and the water droplet itself operates like a prism, splitting up those different wavelengths. That white light contains all the colors, but if you go through a prism, it splits them into that rainbow of colors according to the wavelengths that we saw earlier. So a rainbow is an example of refraction, light bending, going from one medium to another. Another example is a sunset. A sunset is also actually an example of refraction. In this case, it is refraction through the atmosphere itself, that the sun goes down under the horizon, so you're not actually seeing the sun's light directly, but what you are seeing is the sun's light as it's bending through the atmosphere. And the reason that we see red last is because red light bends differently than purple light. So the last light that we see in a sunset has this reddish hue to it. For the same reasons that we see a rainbow, we see a sunset in those beautiful reddish, orangish colors. Another example that of reflection in particular that you maybe haven't thought of before is that really any echo of sound is an example of reflection. We typically think of reflection just always being a mirror, like it's reflecting off. But an echo, if you've ever gone to the edge of a canyon or some other really big room and you heard your voice or your clap bouncing off of a wall somewhere and coming back to your ears, that is an example of reflection as well. It's reflecting off that surface. We use reflection in a variety of different examples. One of which, if you've ever been on a boat that has kind of a sonar system to it, it is sending a wave pulse of sound down to the bottom of the lake or the ocean to bounce back off the floor of that lake or ocean and then be sensed again by that device in the boat. So my friend actually has a boat that has one of these systems, and I can see just how deep the lake is at that given point in time, and we can monitor the depth of the lake at all times. You may have seen ones that are even fancier that can actually sense if there are fish below based on the different reflections that are happening from that sound. All right, the final example that I want to give here is an example of diffraction. We talked about diffraction in terms of waves and also in terms of light with that shadow, but diffraction can also happen with sound. If you sit behind like a pole at a baseball game, It's possible that you can't see what's happening, but you can still hear what's happening. Same thing as if you were standing kind of just around a door frame, you can still hear what's happening inside that room, even though you can't see it. It's because those sound waves are able to bend around the barrier and you can still hear it, even though you don't have a direct line to the source of that sound. So reflection, refraction, and diffraction are occurring all around us, and ways that different examples can happen in terms of light and in terms of sound in our everyday lives.